So, we have looked into the concept of electric double layer yesterday. So, wherein if you immerse a solid object, a solid wall in a fluid which is polar, a polar liquid. For example, you can have an aqueous solution of sodium chloride or potassium chloride. So, the wall will actually acquire a net charge, it could be negative or positive. So, suppose if you consider the wall acquires a net negative charge. So, the positive ions in the fluid tend to migrate and attach as a first layer to the wall. So, this layer is called the Stern layer, and even if you apply an external electric field, this Stern layer appears static and it does not really move along with the fluid. Okay. So, for therefore, practical calculations you do not have to really consider the thickness or what is the effect of Stern layer, but from the Stern layer onwards there is a build-up of positive ions, which is gradual diffusion like process, and therefore, you have a secondary layer called the diffuse layer which builds on top of this Stern layer and extends all the way into the bulk of the fluid. And far away from the wall, the net electrostatic potential difference from the bulk value will be 0. Okay. So, therefore, if you plot the actual potential value right at the wall, you may have a very high value of potential and then slowly gradually decreases, and asymptotically it reaches the value of the bulk potential for large values of y. Okay. So, if you define a over potential which is phi minus phi bulk, okay. So, that gives you the excess potential on top of the bulk, and that value becomes 0 for large values of y. So, therefore, from this we define what is called the d by height, d by thickness, or diffuse layer thickness lambda d, which gives you the distance, approximate distance over which this excess potential decays to 0, right. And the corresponding value of the potential difference, the excess potential from the Stern layer value to the bulk value. So, this is called zeta potential, right. So, the higher the zeta potential, more is the electrokinetic capability of this particular fluid and solid object combination, correct. So, generally one measure is before you check whether you can actually use the phenomena of electrokinetics, you first generally people measure the value of the zeta potential with the electrostatic part of the fluid before applying the electric field, and then they decide whether this fluid and solid combination is good enough to drive the electrokinetics by an external field. Okay. So, I think this part is pretty much clear to you. So, we have taken the example of an aqueous solution of say sodium chloride, and then we said that suppose you assume the bulk which is electrostatically neutral, you have equal number of Na plus ions and Cl minus ions, and also the valence number which denotes the charge will be equal and opposite in this case. Okay. So, therefore, the next part will be to calculate what is the net local net charge density rho e. Okay. So, this is required because we do not know how the potential actually varies. Okay. We are only showing this as upfront, but this is a solution. We have to solve this equation with the appropriate boundary condition, then only we will know that distribution varies like this. All we know is only the value at the wall and the value at large values of y, right. So, in intermediate variation is not clear. So, for that we have to solve the Poisson's equation. So, the Poisson's equation where you have an electrostatic which solves for the electrostatic potential phi. So, is just the Laplacian operator on the left hand side, that is equal to the net charge density, local charge density on the right hand side. Okay. So, to get the local charge density, So, we have to look at all the ions locally. So, the concentration of each individual ion multiplied by the corresponding charge, whether it is positive or negative charge, correct. So, if it is positive, so this will be rho e will be positive and negative and so on. So, and multiplied by what is called the Faraday's constant. Okay. So, the value is given there. So, the question is how do I exactly determine the local concentration. Okay. So, for this we make an assumption of a Boltzmann distribution, so that we can relate the local concentration of these ions to the bulk value C I infinity. Okay. So, through this exponential function, distribution function. So, this exponential distribution function is a function of the over potential, okay, that is phi minus phi bulk. Okay. If your phi equal to phi bulk at large values of y, so this exponential term will become 1 and therefore, C I will be equal to C I infinity. So, therefore, this is a implicit function of y, because here over potential is actually a function of y. So, you can say that C I is a function of y. Okay. So, therefore, once you express this in terms of Boltzmann statistics, we substitute for the expression into the expression for the local charge density, okay, and which looks like this is a pretty straightforward arrangement. Now, we therefore substitute this rho e into the expression for Poisson equation. Okay. So, then the resulting equation is called as the Poisson-Boltzmann equation, because we have the classical Poisson equation into which we put in the Boltzmann approximation, distribution approximation. So, this is called the Poisson-Boltzmann approximation, and as you can see, this is a summation term and this is also a non-linear equation. You have a phi on both sides which cannot be directly solved for, but if you want to solve this with boundary conditions, you have to solve this iteratively. You have to guess the solution and then put this, make sure that you balance the equation. So, if it does not balance, then you re-guess. So, like this is an iterative trial and error process. Okay. So, if you normalize this, you can non-dimensionalize the potential phi as well as the coordinates. So, if you use the following non-dimensional notation, so you can non-dimensionalize phi with multiplying by Faraday's constant divided by universal constant times temperature, and that is your phi star. Similarly, all the coordinates are non-dimensionalized with d by length. Okay. The d by length, whatever expression is shown here, it is coming from simple scaling arguments where you combine all these parameters, so that the units are in terms of meters, okay, and these are a non-dimensional group of different parameters. So, this will be unit of exactly meters. So, if you non-dimensionalize with this d by length, so you get everything in terms of x star and y star and so on. Okay. So, therefore, if you write it in one dimensional notation, suppose if I want to solve the Poisson-Boltzmann equation for just the vertical profile, right, the variation of excess potential as a function of only y for a simple case of a single plate. Okay. So, in this case, therefore, I have to write this Laplacian operator del square p star as only function of y. So, this becomes d square p star by dy star square. On the right hand side, I have the Boltzmann distribution function. Now, this is a nonlinear equation. So, if you want to solve this analytically, so we make an assumption to make this a linear equation. So, how do we linearize this equation? So, we make an assumption that if you look at this exponential term, exponential minus z I phi star, we can use the Taylor series approximation. We can express exponential of x is equal to 1 plus x, and if your x is much smaller than 1, okay, so then this becomes linear. So, therefore, this is what we are going to now do it. So, what we are planning saying that is the fact that Zi phi star is actually a very small quantity compared to 1. Okay. So, Zi is the valence number, okay. It could be plus or minus 1. So, multiplied by phi star, the actual value of phi star, the non dimensional phi is actually a very small value, okay, compared to 1. It is much smaller than unity if you calculate. So, therefore, if you compare the relative order of magnitude of these two terms, you can therefore replace 1 plus x with simply the so this becomes Ci into Zi square. So, we just write this as no, there is some problem here. So, we just okay. So, we ignore all the higher order terms. So, what we are saying is that we have 1 plus x square plus x cube and so on. So, therefore, if this is a small value, all the higher order terms will be negligible. So, your x square, x cube, x power 4 terms will all be negligible. So, therefore, we retain only the term with x power 1. So, 1 plus x is the term that we use, and then if you substitute that, this should come out to this particular form. You have Zi square phi star so we have Ci C star, we have Zi square. Where is f? I think some problem with this formulation here. So, I think there is an f missing, and also this should be 1 plus x. Yeah, I think there is some mistake. Okay. So, now from this point, for the case of Na plus Cl minus, okay. So, we know that Ci infinity for Na plus and Cl minus, they are similar, okay. If you consider 1 millimole solution, so they are each equal to unity, and similarly if you look at the value of Z, they are equal and opposite. So, therefore, if you substitute into this expression, I think then it should be coming out correctly. You have 1 times 1, okay, plus you have 1 times minus 1 square. So, which is 2. So, 2 and 2 cancel, and therefore, you only have phi star. Is that okay? So, you have basically, if you look at aqueous solution of Na plus and Cl minus, you look at only Na plus and Cl minus species concentrations. Okay. So, for that case this reduces to phi star, but I think there is still some issue with the sign, and also it is not, I will get back to you tomorrow on this. Okay. So, how this f is absorbed, it is not very clear. Okay, but from this part you reach the following form, and this is called the d by Huckel approximation. Okay. So, the d by Huckel approximation is actually used for cases where you have equimolar aqueous solutions. Okay. For example, Na plus Cl minus or K plus Cl minus. So, for equimolar, for same values of molarity, and also the valence numbers are equal and opposite. So, for such a limiting case, this summation now drops out, and you have an explicit equation in terms of phi star, okay, and this is called the d by Huckel approximation. Okay. So, we can now therefore solve this d by Huckel approximation, which is nothing but the reduced form of the linearized Poisson-Boltzmann equation. So, we linearize it with this step, where we ignore the higher powers of x and we convert it into this form, but still you have a summation which we reduce it for the case of equimolar aqueous solutions, and then you get the d by Huckel approximation. So, now we can go ahead and solve this particular equation, which is a simple ordinary differential equation of second order. You need two boundary conditions. So, therefore, we can apply the condition that at y equal to 0. So, since this is a non-dimensional coordinates, we can define everything in terms of non-dimensional values. So, you have y star equal to 0, the corresponding value at the wall, the over potential will be the value of phi star naught, okay, or you can use W if you want to represent this at the value at wall. So, what it means is that is the value of potential at the wall minus bulk. Okay. So, this excess potential or over potential is therefore phi star naught, and at large values of y star going to infinity, your excess potential goes to 0, right. So, with these two boundary conditions, if you solve this equation, you have an exponential, you will get an exponential solution. So, that means your phi will turn out to be phi naught exponential minus y by d. So, I will give you a few minutes for you to actually work out. So, you know the solution to this equation. Okay. So, you can apply these boundary conditions and check whether you get this particular solution. Okay. So, once you get this, you substitute into the expression for C from the Boltzmann statistics. So, C in terms of exponential minus z I f phi. So, you substitute for phi into this, and we can write an expression for the concentration of the species in terms of the non-dimensional y coordinate. So, please do these two things. Please check the solution and also get the expression for concentration. So, you have solution as C1 exponential minus plus mx plus C2 exponential minus mx, right. So, at y going to infinity, okay, the exponential mx will also go to infinity, but solution should be 0. So, therefore, the constant C1 should be 0. So, therefore, the solution should be C2 exponential minus mx. So, use the second boundary condition and you will be able to find out C2, which turns out to be phi naught. Okay. And you can write this as y star is nothing but y by lambda d, right. So, therefore, if you substitute this into the Boltzmann distribution for concentration, you can get an elaborate expression for Ci. Is it clear till here? So, this is the solution to the one dimensional Poisson-Boltzmann equation. So, now you know exactly the nature of the electrostatic potential, how it varies with y. So, it is an exponential decay. Okay. So, therefore, if you plot this function phi by phi wall, if you normalize this with the value of phi at wall, so that it fits between 0 and 1, and you plot this as a function of y over lambda d y star. So, you see the exponential variation very clearly. So, for large values of y by lambda d, this value of phi goes to 0. Okay. So, this is basically your excess potential variation. The other is your concentration variation. Okay. So, from this, for a particular species, for Na plus, for Cl minus, for each of this you can plot the variation of concentration with respect to y. Okay. For example, if you have a negatively charged wall, so the concentration of positive charged ions will be in excess close to the wall, right. So, therefore, you see the concentration of Na plus is very high at the wall, and then it progressively decays and then reaches the bulk concentration, which is equal to 1, right. Whereas, for the Cl minus, it is deficient, lower than 1 at the wall, and then increases progressively and becomes equal to 1 in the bulk. And once you know the value of phi, you can also express the local net charge density, because this is expressed in terms of phi from the Boltzmann solution, right. So, and that also can be plotted as a function of y. So, the thick line rho e by f variation is also plotted here. So, therefore, from the one dimensional solution you get a lot of information. So, how the electrostatic potential varies, how the local net charge density varies, how the concentration of these ions can actually vary, right. So, now this is the starting point of looking at electrokinetics. So, still now there is still no kinetics, it is just statics. Okay. So, when we put an external electric field, now what immediately what we can observe is the phenomena of electroosmosis. Okay. So, you apply an electric field along the positive x direction, and this results in the Coulomb force. So, this is denoted by this notation F Coulomb, this is the Coulomb force, which is equal to the local charge density rho e times the electric field. Okay. So, therefore, you have the electrostatic potential like this. So, you have a variation up to the d by length, beyond which the value becomes 0, excess potential value, and it is symmetric. So, this is a case of flow between two parallel plates. So, you will have a symmetric distribution about the center line for the electrostatic potential. And now, if you therefore apply an electric field, what happens? So, you have the electric force, the acting in the momentum equation will be rho e times E. That means, wherever you have the local net charge density value positive finite value, so there you will experience an acceleration. Okay. So, according to this expression, if you look at rho e, this is a very strong function of phi. Okay. So, wherever you have large values of phi, so that is where the local charge density also will be quite significant. Therefore, close to the wall is where all the force is exerted, and if you move away from the wall where potential becomes 0, there is no force. So, therefore, you can actually divide this problem into two regions. One problem which is an inner problem, which is close to the wall, where you consider only the diffuse layer. Okay. Solve for this separately, try to get the velocity field in the diffuse layer, and then you go to the second region which is the outer region, which is not influenced directly by the electric field, but by applying the velocity as a boundary condition. Okay. So, therefore, so the electroosmosis problem can be divided into two sub problems. Okay. One, we have an inner solution, the inner solution is only for the EDL. Okay. Then we have the outer solution where you have the bulk fluid which is electroneutral. So, if you want to write down the Navier-Stokes equation for the inner solution, okay, now you might ask a question whether we are talking about d by length of the order of tens of nanometers, whether we can use the continuum equations. But again you should remember that the mean free path is also very small for the liquids. Okay. So, therefore, you might be still in a Knudsen number range which is much lesser than 0.1. So, you do not have to really worry about breaking the continuum assumption, whereas for the same length scale, if this was gas flow, definitely no, correct. So, the same continuum Navier-Stokes equation is written. So, you have the time derivative, you have the convective acceleration, pressure gradient, viscous diffusion, plus you have the Coulomb force which is the driving force in this region. Okay. So, here the electric field is applied externally, it is not what is coming internally, this is an external electric field. So, therefore, this is denoted as E external, and this is acting only on the EDL. So, we solve this for the EDL. Now, when you solve this, we make some more assumptions to get analytical solution, that is we want to look at fully developed velocity profile in the inner region, so that the convective acceleration becomes 0, and we are also looking at steady state solutions. So, the entire left hand side, the entire acceleration term on the left hand side goes to 0. Okay. Therefore, also when you are applying this for a plate where there is no pressure gradient, right. So, therefore, dP by, so this solution is now up not for a channel, we are doing this only for one plate. So, this is like a flow past a plate. So, in this case there is no pressure gradient. So, your delta P also becomes 0. So, only two forces are there, one is your viscous force, the other is your Coulomb force. So, these two will perfectly balance and you get the velocity profile out of this momentum balance. Okay. So, therefore, the other terms are all 0, assuming you have fully developed steady state solution for a flat plate with 0 pressure gradient. Okay. So, now we substitute for the Poisson's, we know the Poisson's equation. So, we can actually write your rho E. So, please correct this, this is not, it looks like P E, but it is actually rho E. Okay. So, this is rho E, right. So, this rho E is actually rewritten from the Poisson's equation as epsilon into del square phi. So, we just substitute for that into the term rho E on the right hand side, and therefore, if you express this, this becomes, this is your kinematic viscosity times d square u by dy square minus epsilon permittivity into d square phi by dy square. This is coming from the Poisson's equation into the external electric field. So, now if you integrate this as a function of y, okay, so you get the following solution for velocity profile as a function of phi and y. Okay. So, therefore, if you apply the no slip boundary condition at the wall, y equal to 0, the velocity is 0, then you finally end up with the solution in the inner region for the velocity profile. Okay. So, this turns out to be simply epsilon E times phi by eta, okay. And we also apply the condition that at y equal to 0 your phi becomes phi naught, right, that is your value of phi at the wall, okay. So therefore we get this particular solution for the velocity profile. So if you plot this velocity profile, so this is how it varies. So it is a kind of a linear variation with respect to phi, right, and how does phi vary? Exponentially. So therefore as a function of y, u will also be exponential variation, okay. So having known the inner solution, now we do not have to again come back to this. So we can assume that the outer solution is driven by a solid wall with velocity of this particular value. So basically the EDL is a very thin layer close to the wall, right, so few nanometers. So since we have the velocity profile for the EDL, okay, so at the edge of the EDL we can apply this as a boundary condition, and we can see that the entire bulk flow is driven by the motion of the EDL. So the edge of the EDL can be assumed to be a wall which is moving with a particular velocity given by this value, okay. So this will be like a couette flow, okay. So you have the bottom wall at the edge of the EDL which is moving, top side also at the edge of the EDL there is another wall moving with the velocity, and therefore the bulk value will be nothing but the average value between the top and bottom. So if both of these values are same, so you have the value of the bulk velocity also same as the boundary values, okay. So this is basically what we now translate this solution into a slip boundary condition, okay. So for the outer solution we solve the routine Navier-Stokes equation, there is no Coulomb force on that because the net charge density is 0 there. However, we apply a slip boundary condition, okay, with the same velocity what we got from the inner solution, right. So therefore the value of velocity that we apply will be equal to this, because if you write down the solution for u inner at y equal to lambda d, right. So that is the edge of the EDL. So at that point you can assume your phi to be approximately 0, excess potential almost reaching the bulk value, so it is 0. So therefore this turns out to be minus epsilon phi naught E by viscosity. So this will be the slip boundary condition that you give for the outer solution. So this slip boundary condition is called Smoluchowski slip, but since we apply it for the case of electrokinetics, this is called Helmholtz-Smoluchowski slip boundary condition. We have the same Smoluchowski in the gas flows for temperature also. Temperature slip is also called Smoluchowski. So for the case of electrokinetics we call this as Helmholtz-Smoluchowski slip boundary condition. So therefore for the outer flow, if you assume you have acceleration, you have pressure gradient, you can include all of this and you can solve this, right, with the slip boundary conditions, alright. So you do not have to basically ignore delta p, because still this is a channel flow, so delta p will be there. So you may have delta p, you have the viscous diffusion, you may also have the developing region where the inertial terms cannot be neglected. So if you want to get the full solution, you can go ahead and still solve it in a conventional way, but with the following Smoluchowski slip boundary condition at y equal to 0. For the limiting case where your delta p equal to 0, you have a fully developed profile, you have a steady state profile, okay, then what will be the value of bulk velocity? same as that of the boundary condition. So, there you will have all these terms going to 0, you have d square u by dy square equal to 0. So, this will give you a linear profile. So, since you have a same value of velocity at y equal to 0 and the top wall, so this will therefore become equal to the value at the boundary itself, all right. Okay. So, that will become your Couette flow solution. Okay. So, this is all about the electroosmosis. Okay. So, you have any questions or doubts on this? So, the entire electroosmosis is now broken into two sub problems, one where we find solution for the inner region, use that as a boundary condition for finding solution for the outer region. Okay. So, what is the application of such kind of electroosmotic flows? So, one is when you design what are called electrokinetic pumps. Okay, these are not conventional mechanical pumps where you drive flow by purely pressure gradient. Okay. So, these are flows where you can have simultaneously both electroosmotic driven flow plus also a pressure gradient driven flow, right. Whereas, if you take pure channel case, you have only a pressure gradient which drives the flow there. Okay, it is a pure mechanical pumping process. Whereas, in the electrokinetic pump we also use the electroosmotic motion for creating flow, right. So, therefore, if you want to develop one such application of this electroosmosis, it is in designing an electrokinetic pump. Okay. So, we therefore apply an electric field along a capillary. So, capillary means it should be of the order of few millimeters, so that you get a strong electroosmotic motion, and you also generate flow, and there is also a pressure gradient which is driving the flow, right. This is a channel case. So, if you suppose apply an external electric field, E is equal to delta V by L, potential difference over a length L, and you assume the rectangular micro channel to be of depth 2D, width, length and cross sectional area and so on. Okay. And therefore, in this case, so you do not have to directly assume a pressure gradient right away, okay, but you can also have this, and you also make sure that your d by length is much smaller than your depth or the height of the channel, okay, and this height should be lesser than the width, so that it can be made a 2-dimensional assumption, okay, and this width should be lesser than L. Okay. So, therefore, for a 2D system, the electroosmotic and pressure driven flow. So, if you want to calculate the flow rates, okay, so how do you get it? So, for the electroosmotic flow, you integrate. So, you have the velocity at the wall, which is your boundary condition, and if you solve the bulk value also without any pressure gradient. Okay. So, what happens? As I said, you get the same bulk value as the wall. So, therefore, it is nothing but your wall velocity which is uniform throughout. So, if you integrate this from minus d to d across the entire channel height, so you get your net volumetric flow, right. So, this is the component coming from the electroosmotic process. Okay. You can also have a pressure driven component as well. Suppose you assume that there is only a pressure gradient which is driving the flow, okay, and there is no electroosmosis. Okay. In that case, you put your E as 0, your external electric field, you compute your conventional solution for flow in a channel with a pressure gradient. So, in that case you get your classical solution. So, this pressure driven flow is I think all of you know this is for a channel case. Okay. So, now if you therefore look at a generic capillary, okay, you can have both of these combinations, a portion of this coming from the first term, the portion of this coming from the second term, because the first term we got by neglecting the pressure gradient completely, second we got by neglecting the complete electric field, but the actual case will have both of these governing the flow. Okay. So, therefore, the total flow rate Q, if you integrate this, you will be able to get an expression of this particular form, right. So, it is driven by both the slip velocity at the wall, which is nothing but the electroosmotic solution for the EDL, and the pressure gradient. So, this is the mechanism of the electrokinetic pump. Okay. So, you have both these contributions coming to pump the flow. Okay. So, you can have two limiting cases as I said. Okay. So, you can have two limiting cases, one in which the pump works where you have a full flow without any pressure gradient, that is only by the electroosmosis, and the second case where there is no flow, but only pure delta P, that means you close the exit, you cause the maximum pressure rise to happen. Okay. So, that means there is no outlet for the flow to go, but you have the maximum pressure rise. So, these are the two extreme cases. So, therefore, we can find out the solution for the two extreme cases. For example, the second case where your Q outlet equal to 0. So, we have to put the condition, since Q equal to 0, from this expression, second expression, we should be able to find a relation for delta P, because we know the solution U wall. So, U wall I am substituting into this expression and getting a solution for delta P. Okay. So, you can so this is one solution. The other solution is where you have the maximum pressure rise. Okay. So, the maximum pressure rise can also be obtained. Okay. So, what it says is you can therefore calculate what is the thermodynamic efficiency for a particular pump which has both these contributions. You can have the electroosmotic and also the pressure driven contributions. So, how do you define the thermodynamic efficiency? Whatever pumping power that it generates divided by what is the total input power to the system. The total input power is the external electric field. So, that is your delta V times I. Okay. And whatever pumping power it generates is your delta P times Q. Okay. Q is the volumetric flow rate, delta P is the pressure drop. Okay. So, with this you can actually check the different modifications to this electrokinetic pump and see whether you can improve your thermodynamic efficiency. Usually the efficiencies for these kind of pumps are very low, okay, less than 10%. Okay, but nevertheless these are an alternative way of pumping apart from using a mechanical pump external, right. So, you just supply an electric field and then you drive the flow. So, this is not a bad idea if you want to drive very small flow rates, but the efficiencies are also very less, of the order of less than 10%. Okay, so, we will stop here. So, tomorrow in the next class on Tuesday, we will look at the second portion of the electrokinetics, which is called the electrophoresis. So, the electrophoresis is kind of an extension to the electroosmosis, because in the electroosmosis case your walls are stationary and the fluid is moving. Okay. In the case of electrophoresis, we assume these particles, we apply this primarily to particles. So, you can call this as particle electrophoresis. So, these particles are actually moving due to charge accumulation around these particles. So, when you put an external field, okay, so these particles actually move. So, you can assume that the bulk fluid is actually not moving, but the charges are all concentrated around these particles, and these particles actually move relative to the bulk fluid. So, this is what we are going to study, and this is quite important when you consider particle dispersions in fluids. So, most of the times these particle dispersions also have a electrostatic potential. the electric double layer formation is there. Okay. We may not be able to see it, but definitely if you put an electric field you will find all of these particles will start migrating. Okay. So, this is also a very important phenomena when you consider say nanofluids, right. So, just quickly the same theory whatever we applied for calculating the velocity, we will apply that here also. We make an assumption that the particle and the debye layer everything moves together, okay, so that there is no slip between the particle and the debye layer. So, whatever solution we got for the debye layer velocity will also be directly applied to the particle here. Okay. So, we will quickly wrap up this case and then I will briefly introduce the equation for solving for the concentration, the advection diffusion equation for concentration of the species. Okay. Because the earlier case the Boltzmann distribution function can be used, but the actual distribution will be more complicated if you have a flow, right. So, if you have a flow it is not a simple the Boltzmann distribution is there for the static fluid, but the actual concentration will also change if you have a motion. So, in that case we cannot use only that. So, we have to solve for the advection diffusion for the concentration and get the actual value of concentration. So, this is given by what is called the Nernst-Planck equation. Of course, so they are detailed topics, I do not want to spend a lot of time because our emphasis is to look at heat transfer. I am just giving you some overview of this. So, if you take a course on microfluidics for example, so these are usually covered in a greater detail. There are also other phenomena like dielectrophoresis, dielectrotachophoresis. So, they are all phenomena which are emerging areas of research. Okay. So, but I also do not want to talk about them in this basic course because the most commonly used electrokinetic mechanisms are these two, okay, osmosis and electrophoresis. In heat transfer you have a equivalent to this is called thermophoresis. Okay. So, you have a temperature gradient which is driving the motion. Okay. So, you have thermophoretic pumps similar to electro-osmotic pumps. Okay. So, but however, those kind of phenomena with thermophoresis can appear at even large scales. It depends on the temperature gradient. Okay.